Hi everybody, we will talk about the uniform continuity. Mainly I will follow the Wikipedia page of this uniform continuity. And we will talk about the definition, the difference between uniform continuity and ordinary continuity, and two simple conditions that we can detect easily, the uniform continuity with two examples. And then I will prove one function that is uniformly continuous, and I will show that one function is not uniformly continuous. Okay, let's get started. The definition is a real function f on real numbers is said to be uniformly continuous if there is a positive real number delta such that the function values over an interval of the size delta are as close to each other as we want. Here there are a couple of keywords, as close to each other as we want, and a small number or a real number delta. This suggests that our good old friend, the epsilon delta definition, right? But the meaning is that here we have a function, a real function, defined on real numbers, of course, a subset of these real numbers, and we, for any epsilon, right, given epsilon, we wish to the numbers, we wish to values of the function as close as epsilon if we take two elements from the domain that is apart at most delta. That's, we define a delta interval here. The length of this interval is delta, and if we take any two numbers here, say x and y, the distance between fx and fy on the function are at most epsilon. If this condition is satisfied, we say that this function is uniformly continuous. So the formal definition, as we'll follow this observation, is, and it's like that. For a function f from d to r, and d is subset of r, and for any epsilon greater than 0 given, and for any xy in the domain, if we can find a delta positive such that the distance between x and y is less than delta, then fx and the distance between fx and fy is less than epsilon. If this condition is satisfied, we say that f is uniformly continuous. So what is the difference between uniform continuity and the ordinary continuity? The definition of the ordinary limit is a function should take its limit value at a point, right? If the limit of fx as x goes to a is equal to fa, then we say that this function is continuous at the point a. And the definition of the limit is for any epsilon positive, we can find a delta positive such that the distance, if the distance between x and I is less than delta, then the distance between fx and fa is less than epsilon. So this is the definition of the ordinary limit. In the ordinary continuity, in the uniform continuity, we have a delta that works at any point a, right? At any point a, we can find a delta. It will work at any point a that f is continuous. But in the ordinary continuity, at different levels, we may need different deltas, right? At different points, say at point A, we can find a delta A, and we say that this function is continuous at a point A. At another point B, we can find another delta B, and this simply doesn't work. We will see an example of this. This is the difference between the ordinary continuity and uniform continuity. And now we will present two simple facts that we can easily detect a function that a function is not uniformly continuous. A continuous function is not uniformly continuous, basically. First condition or first statement is that if a function is unbounded on a bounded domain, then we can say that this function is not uniformly continuous. The example is fx is equal 1 over x function. Remember the graph of this function. It's like that, right? And it is unbounded on a bounded domain. If we take the domain, the interval, the closed interval 0, 1, in this interval, this function is not bounded, right? And this function is not uniformly continuous. Another example or another condition is if the slope of the function on a unbounded, the slope of the function is unbounded. For example, it goes to infinity on a bounded domain. And the example here, the function of y is equal x square. And if we think the graph of this function, you can see that this is, let's say the domain is 0 to infinity. It's an I have a mistake here. This is not a bounded. This is an infinite domain. This should be an infinite domain. On an infinite domain. Here we have an infinite domain. The interval 0 to infinity, and the slope of this function is constantly increasing, and it's not bounded. It's always positive and it's always increasing. So it's unbounded. So this function is also not uniformly continuous. But these two are continuous functions, right? We know them very well. They are continuous, but they are not uniformly continuous. So let's see two examples with proofs and definitions of uniform continuity. One would be the y is equal x to the power 2 function, x square function, and the other one square root of x function. One is uniformly continuous and the other one, this one, is not uniformly continuous. The first example is a uniformly continuous function. Fx is square root of x function. As always we do in epsilon delta definitions, we should focus on an observation, and we should focus to find a delta. The delta, probably it's a function of epsilon, and then we would show that if the distance, in this case x and y, is less than delta, then fx and fi, the distance between these two values, should be less than epsilon. Okay. First we should concentrate to find a delta that satisfies this, but first we need to analyze this part, right, to come up with a solution of the delta. Here we want the square root of x minus square root of y should be less than delta. Okay, and it's not so easy. If you see the solution, it's easy, but finding this thing can be a little bit tricky. And this should it's work if we take delta is equal the square of the epsilon. Okay, let me demonstrate the result of my observation here. If we take the distance x and y less than delta is equal epsilon square, so we should write it a little bit properly. For epsilon greater than 0 given, pick or choose delta is less than epsilon square or equal epsilon square. Okay, and now we are sure that the distance between x and y is less than delta, and it's less than epsilon square. And we can write x minus y as this is equal square root of x minus square root of y times their addition, right? We know that. Now we want to reach an inequality contains this, and we need to find something for this term, and it's easy. Actually, we can use the triangle inequality in the form that, remember that if the distance, we know that a plus b, absolute value of a plus b should be greater than the distance of absolute values of a and b in absolute value, right? Remember this inequality. But in our case, x and y is always positive, so we can write this. The absolute value of square root x plus square root y is greater than, this term would be again square root of x, and this will be square root of y. So we have this equation here, right? X, this term is greater than this one. So we can write this times, we replace this one with a smaller value. But this writing is not maybe not correct. We should write this as like that. The distance between x and y so if we replace this one with this term, we have a smaller value from x minus y, right? So we should write it like that. The square root of x minus square root of y times absolute value of square root x minus square root y is less than or equal to x minus y, right? We know that, sure, because we replaced this term with a smaller one, and this will became smaller than x minus y, but we know that this is less than epsilon square, and here we have the square of square root x minus square root y. This is less than epsilon square, and this implies that square root x of x minus square root of y in absolute value is less than epsilon, and that's what we want to achieve, right? And as a result, we can say that the square root of x is uniformly continuous. The thing here, if you think the graph of this function for any epsilon, say that given this interval is epsilon length, we can find the delta, in our case epsilon square, if this distance is less than epsilon square. If you pick any two numbers here, the distance between these two should be less than epsilon. Okay, we can prove this actually. Basically, we proved this observation formula here. The second example is fx is equal x to the power 2. This function is not uniformly continuous, and we can see that we can prove it by contradiction, by reaching a contradiction. Suppose it's uniformly continuous, right? Say that on the contrary, f is uniformly continuous. Then we should, for any epsilon given, right, and say epsilon positive given, then if this is uniformly continuous, we should have a delta, a corresponding delta positive, and this will satisfy all the conditions, right? For any x and y, if the distance between these two is less than delta, then the distance between fx, in our case x squared minus y squared, is less than or equal to epsilon. This should be true, right? So the problem here is the x squared minus y squared in absolute value is equal x minus y times x plus y. We cannot limit this value, because on the real axis we can go at the infinity as much as we want, and then this term will be getting greater and greater. It does not an upper bound, so we can make this term larger and larger, and eventually we can make it greater than epsilon for any delta. So the observation is this, and we can make it we can write it formally like that. Say that we have a delta, and the distance between x and y is less than delta, but we can pick x and y as greater than delta over 2, right? We have an interval, and the distance, the length of interval is delta, and for any x and y in this interval, this statement should be true. But we can make the distance between x and y is greater than delta over 2, right? This is our legitimate right. We can make this. And on the real axis, we can go to right and pick x and y to satisfy that x is greater than epsilon over delta. These two are definite and they are positive numbers. For sure we can make it x is greater than this value, and also we can make y is greater than epsilon over delta. Now let's write the definition. The distance x and y is less than delta. This is correct. Does it imply that the multiplication of x and y and x plus y, which is basically equal to this one, is less than or equal to epsilon? It's actually not. So we can find for any epsilon and delta, we can make it happen, right? The x minus y is less than delta. You know that. And x plus y, this is greater than or equal to delta over 2, and x plus y is greater than 2 epsilon over delta, right? And this multiplication is greater than epsilon. So this can't happen. This is a contradiction. So we can say that fx is x squared is not uniformly continuous.